The Chevrolet Cobalt is east of the tornado at 6:03 p.m. This is where it is supposed to be. East of a tornado in western Oklahoma means you are ahead of its direction of travel, in position to observe and measure, with the road behind you clear and the road ahead clear, and the storm to the northwest where all of the tactical training and the accumulated experience of 2 decades says storms in this part of Oklahoma in late May are supposed to stay. 3 people are in the car. Tim Samaras, 55 years old, is in the passenger seat. Carl Young, 45, is in the vehicle. Paul Samaras, 24, Tim's son, is in the vehicle. Between them, they carry more than 3 decades of active tornado fieldwork, more than 125 tornado intercepts, the Guinness World Record for the greatest pressure drop ever measured inside a tornado, and the TWISTEX instrument probes that have been collecting atmospheric data from inside violent tornadoes since 2003, data that no other scientific program in the world has figured out how to collect. This is where it is supposed to be. The methodology has placed them east of dozens of tornadoes before this. It worked every time. The methodology is about to encounter something it was not built for. A tornado that is expanding its width from 1 mile to 2.6 miles in roughly 30 seconds. A tornado that is turning left toward the south when the entire behavioral framework of right-moving supercells says it should track northeast. A tornado that is generating subvortices, smaller embedded circulations with their own extreme wind speeds that extend the effective hazard zone well beyond what any radar return visible to the chasers shows. The Cobalt is east of where the tornado is at 6:03 p.m. By 6:15 p.m., the tornado is where the Cobalt is. When the car is found afterward, it is half a mile from the position where the team last transmitted. This is the story of the 3 people who were in that car, not the story of the tornado, the 2.6 miles, the left turn, the subvortex science, though those things matter and have been told. This is the story of who they were before they drove east on May 31, 2013, and of everything they had done in the years and decades before that afternoon, and of what the world lost when their car came to rest half a mile from where it had last been in contact. It is the story of the most consequential scientific field team that tornado research has produced, of the instruments they built and the data they collected and the record they set, and of the specific day, 11 days before El Reno, when the most experienced of them looked at a different tornado and made the judgment that it was too dangerous to chase, and of the day 11 days after that, when they went out again. And the tornado was different from what the available data said it was. If this kind of deep, real science holds your attention, take a second to like and subscribe. It genuinely helps. Let's begin with who they were. Tim Samaras was not a meteorologist. He was never a meteorologist, and the distinction matters because what he became in tornado science was not a product of formal training in the discipline. It was a product of an engineer's specific way of seeing a problem, not what is happening, but what can be built to measure what is happening, applied to the most data-sparse environment in atmospheric science. He was born in 1957 in Denver, Colorado, and he grew up fascinated by things that produce effects larger than themselves: lightning, which releases more energy per second than most power plants, weather systems, which reorganize the atmosphere on continental scales, and tornadoes, which concentrate that atmospheric energy into a rotating column less than a mile wide and kill people in seconds. He was also an avid amateur astronomer, a person who spent nights in the dark of the Colorado high desert pointing a telescope at objects millions of light years away, who understood patience as a scientific practice rather than merely a virtue. Astronomy teaches a specific relationship with phenomena that operate on their own schedule. You cannot rush a galaxy, and you cannot manufacture a clear night, and you cannot will a good alignment into existence. You prepare, you wait, you are there when the moment arrives. Tim Samaras brought this specific patient readiness to tornado science. He was also fascinated by electronics and invention, by the puzzle of building something that works where nothing before it has worked, by the engineer's specific question, what can be designed to do what has not yet been done? His day job was at first the Denver Research Institute, and later Applied Research Associates, where he worked as an explosives expert. This is not a minor biographical footnote. The skills that made Tim Samaras indispensable to his employer. Precision engineering of instruments and enclosures that must withstand extreme forces, ballistics calculation, the specific practical science of how solid objects behave under violent dynamic loads, are exactly the skills that would allow him, working on his own time, to design a tornado instrument probe that could survive the direct passage of a violent tornado and keep recording through it. The intersection of explosion engineering and tornado science is not accidental. Both domains require building things that are meant to survive force magnitudes that standard engineering frameworks were not designed around. Tim Samaras did not become an instrument designer for tornado science in spite of being an explosives expert. He became one because of it. He thought about extreme forces the way other people think about moderate ones, as a normal engineering parameter to be accounted for and designed against. He began chasing tornadoes in 1991, originally drawn not to the storm itself, but to the lightning that storm systems produce. Lightning was his first research focus. He photographed it, studied its electrical behavior, and worked to understand the electromagnetic spectrum of a lightning strike in ways that standard weather observation did not capture. The transition from lightning to tornadoes was not a sharp pivot, but a gradual expansion. Tornadoes occur in the same supercell systems that produce the most intense lightning, and a researcher already positioned to chase supercells for lightning observation has only to redirect their attention slightly to find themselves in the tornado problem. In the early 1990s, Tim shifted his primary focus from lightning to tornado interior measurements, and the engineering problem he was trying to solve crystallized into its specific form. Design an instrument that can be placed in the path of an approaching tornado, survive the passage, and record the atmospheric conditions that no other instrument survives long enough to document. The problem with measuring a tornado from inside it is that nothing built for standard meteorological measurement survives the experience. Weather balloons dissolve in the updraft. Data loggers not specifically designed for the mechanical environment of a tornado are destroyed by the wind forces or the debris impact before they can record what they need to record. Placing a standard weather station in the path of a tornado and hoping it survives is not a measurement strategy. It is an experiment in which the failure mode, debris impact or wind pressure or structural failure of the enclosure, is determined before the deployment begins. And the answer is almost always debris impact. The measuring environment that Tim Samaras was trying to instrument is, by definition, one of the most mechanically hostile environments that exists at the surface of the Earth. His engineering insight was that the instrument's shape could be optimized against these failure modes in the same way that explosive enclosures are designed against blast environments. He started building the first version around 1999. The HITPAR hardened in situ tornado pressure recorder was the answer Tim built over the course of the mid to late 1990s. The first version was ready around 1999. Its design philosophy was visible in its shape: a squat, wide, low-profile device, roughly 50 pounds in weight, roughly resembling a traffic cone that had been melted flat onto a hot surface. The squat shape was not aesthetically incidental. It was aerodynamically calculated. The low center of gravity resisted the lateral forces that would flip a taller instrument. The flat base maximized contact area with the road surface and maximized the friction force that would hold it in place. And the overall geometry minimized the surface area exposed to aerodynamic lift. Inside the armored casing, sensors measured atmospheric pressure, temperature, and humidity at 10 samples per second, alongside cameras designed to capture visual confirmation of the probe's location relative to the tornado's core. The casing itself was engineered against debris impact, using the same principles that Tim applied in his day job. The instrument was expected to be struck by debris moving at F-scale wind speeds, and expected to keep recording through the strike. The turtle probe, as the instruments came to be called, for their shape, was the right instrument for the problem. Whether it could be deployed correctly in practice was a different question, and it was the question that the 3 seasons before Manchester answered very nearly, not quite, almost, close enough to be frustrating, but not yet. He began chasing tornadoes in 1991. In the years before mobile internet, before smartphone navigation, before the real-time radar access that modern chasers take for granted, storm chasing required physical preparation, road knowledge, and the specific intuition that comes from spending thousands of hours in the atmosphere watching it behave. Tim developed that intuition over the course of the 1990s, while simultaneously developing something else, a framework for what he specifically wanted to do, which was not just to observe tornadoes but to measure them from inside. For 3 years after the first probe was ready, Tim Samaras tried to deploy it in front of a tornado violent enough and close enough to provide meaningful data. For 3 years, the combination of weather pattern, storm behavior, road network access, and tornado track conspired against him. The 2001 tornado season was quiet. The 2002 season offered opportunities that did not produce the specific intercept geometry he needed. Tornadoes that tracked over terrain without the road network access required for close positioning, or storms that intensified too rapidly for a precise deployment, or intercept opportunities that closed before the team could reach the positioning window. Tim and the small team working with him on the project, funded in part by the National Geographic Society, which had become interested in his work, chased tornado after tornado and came back without the data. National Geographic photographer Karsten Peter, who was documenting the project for the magazine and whose published work in the April 2004 National Geographic would eventually tell the Manchester story to the magazine's worldwide audience, had lived through those 3 seasons of near misses. He called for extensions of his assignment when the season was ending without the deployment that would justify the story. The extensions ran out. The season ended. He called again. 3 years of chasing a specific deployment geometry with instruments built specifically for it, funded by a magazine whose editorial patience has limits, is not a casual or incidental investment. It is the specific professional bet that someone makes when they are certain enough of an idea that they will accept repeated failure in pursuit of a single confirmation. Tim Samaras' specific certainty over those 3 seasons was that the turtle probe could survive direct passage of a violent tornado and provide data that no other instrument could obtain. He was right. He was just not yet right in a way that the external world could verify. Then came June 24, 2003, in eastern South Dakota. Then came Probe 3 at the intersection of 207th Street and 425th Avenue. Then came the 100 millibar pressure drop in 12 seconds. The day is known across South Dakota as Tornado Tuesday. 67 tornadoes developed across the state in a single afternoon, the highest single-day count in the state's recorded history at the time. Tim Samaras and his team were in the field, as they had been every viable day of the season, and they found themselves tracking a storm developing southeast of Woonsocket that was showing every radar characteristic of an intensifying supercell capable of producing a violent tornado. The storm turned southeast, then south. The road network Tim had studied and mapped for years in exactly this kind of situation, county roads that run straight and long across the South Dakota prairie, accessible at 90-degree intervals, offered intercept geometry that was workable. The decision to deploy was made in the car, in motion, with the tornado visible in the distance and the Doppler returns showing the rotation tightening. Tim had been in this specific situation, promising intercept, workable road, probe in the back of the vehicle, dozens of times in the 3 prior seasons. Each prior time, something had prevented the deployment from capturing what it needed to capture. The tornado had deviated from its expected path, or the road network had not permitted close enough approach, or the tornado had been weaker or shorter-lived than the setup suggested, or the timing of the probe drop relative to the tornado's arrival had been off by enough to miss the core. On June 24, 2003, Tim turned onto 425th Avenue and dropped Probe 3 at the intersection with 207th Street. He placed the instrument within approximately 100 yards of the tornado's anticipated track. He drove north. The F4 tornado, winds between 207 and 260 miles per hour on the original Fujita scale, a tornado rated at the second highest category of destructive power on the scale Tim's instruments were designed to measure, tracked directly over the probe 82 seconds after Tim placed it on the road. In those 82 seconds, Tim drove far enough north to be outside the direct path of the circulation. He watched through the windshield as the tornado passed over the probe's location. He did not know yet whether the probe had survived. He did not know yet what the probe had recorded. He turned south when the tornado had passed and found the instrument still on the road, intact, still running, still recording. The data the probe had captured in the seconds when the tornado passed over it showed a drop of 100 millibars of atmospheric pressure in approximately 12 seconds. 100 millibars. To understand what this number represents, the normal atmospheric pressure at sea level is approximately 10 and 13 millibars. The difference in atmospheric pressure between sea level and an elevation of approximately 3,000 feet is roughly 100 millibars, the amount of pressure that changes as you ascend the height of a small mountain. The F4 tornado that tracked over Probe 3 on June 24, 2003, produced a pressure deficit of that magnitude not over a vertical ascent of 3,000 feet, but in the horizontal distance across its rotating core, in 12 seconds at the surface of the Earth. This is what a tornado is in the language of atmospheric physics, a column of air rotating so rapidly that the centrifugal force of the rotation has created a pressure deficit at the center that is equivalent to climbing thousands of feet of altitude, except that this deficit exists at ground level, in the horizontal plane, within a column a fraction of a mile wide. Tim Samaras had always known this, in the way that tornado scientists know it, but knowing it in the abstract and measuring it directly in a data set that no other instrument had ever produced are categorically different things. The pressure trace from Probe 3 on June 24, 2003 is the first direct measurement of the thermodynamic interior of a violent tornado at the surface. The kind of data that atmospheric models had been parameterized from theory rather than observation, because observation had not previously been possible. The Guinness World Record for the greatest pressure drop measured in a tornado was entered using Tim Samaras' data from Kingsbury County, South Dakota. The record has not been broken. No other researcher has placed a probe in the core of a tornado of comparable intensity with comparable instrumentation and retrieved the data intact. The reason is the same reason it took Tim Samaras 3 years and 18 National Geographic grants, and the accumulated intuition of a decade of storm chasing to capture it once. This is extraordinarily difficult. The opportunities are rare. And getting it right requires a combination of engineering, science, field judgment, and luck that did not come together a second time before Tim's death ended the program that made it possible. Karsten Peter, the National Geographic photographer who had been documenting Tim's project through those 3 years and was present at Manchester, also deployed a custom-built camera probe of his own in front of the tornado. The Nat Geo probe was found 450 feet from where it had been placed after the tornado moved on. Tim's probe 3 was found where he had placed it. The difference in probe survivability was the engineering. He described the Manchester intercept as the most memorable event of his career. The National Geographic feature that followed the Manchester intercept appeared in April 2004 and introduced Tim Samaras to a public audience beyond the small scientific and storm-chasing communities that had known his work. The story of the probe, the 3 years of failure, and the 12-second recording that set a world record was the kind of narrative that the magazine was specifically suited to tell. The long, patient pursuit of a single data point that no one else had been positioned to collect. National Geographic would go on to fund Tim's work through 18 separate grants. He was named a National Geographic Emerging Explorer in 2005. He co-authored a book, Tornado Hunter, Getting Inside the Most Violent Storms on Earth, published in 2009. He authored or co-authored approximately 12 peer-reviewed scientific papers. And in 2009, when the Discovery Channel launched a reality television show called Storm Chasers, documenting tornado research teams in the field, Tim Samaras and his TWISTEX colleagues became, briefly, television personalities. TWISTEX, Tactical Weather Instrumented Sampling in/near Tornadoes Experiment, was the formal name Tim gave to his field research program after the Manchester intercept made external funding and formal scientific collaboration both feasible and necessary. It was a deliberately collaborative effort, a loose confederation of scientists, meteorologists, and engineers who fanned out across the tornado-prone landscape of the central United States and Chevrolet Cobalts, with specific assignments and coordinated communication. The TWISTEX team at its full operational complement included Dr. Bruce Lee and Dr. Kathy Finley from the University of Northern Colorado, who had developed the collaboration with Tim in the early years, Tony Laubach, a meteorologist who led the Mesonet operations, and a rotation of Iowa State University students who participated in field seasons as part of the project's educational dimension. Tim Samaras was the director. Carl Jung was in the core intercept vehicle with Tim. Paul Samaras joined the operation as it matured. The structure of TWISTEX was designed around a specific scientific goal that was more complex than it appeared from the outside: to obtain simultaneous measurements of the conditions inside a tornado and in the atmospheric environment surrounding it, at multiple points and multiple distances, assembling a three-dimensional picture of the tornado's thermodynamic relationship with the air it was embedded in. The intercept vehicle, Tim and Carl, with the turtle probes in the back, was one node in a larger measurement network. The mesonet vehicles were positioned behind and around the storm, measuring the boundary layer conditions in the storm's inflow, tracking the temperature and humidity gradients in the air being drawn into the circulation, building the environmental context that gave the interior measurements their meaning. This is what the television cameras did not show. The Discovery Channel's Storm Chasers, which ran for 3 seasons from 2009 to 2012, focused on Tim and Carl in the intercept vehicle, the dramatic close approaches, the probes placed on roads in front of approaching funnels, the narrow escapes. It was honest television in the sense that those things genuinely happened, but it left out the context that made them science rather than spectacle. The distributed team of researchers coordinating by radio from positions miles from the tornado's core, collecting the surrounding environment data that gave the interior probe readings a framework for interpretation. One consequence of the television show's framing was that the scientific public and the broader public came to understand TWISTEX as a program about getting close to tornadoes. Tim Samaras understood it as a program about answering specific scientific questions about tornado genesis, about the thermodynamic exchanges at the boundary between the tornado's circulation and the atmospheric environment it drew from, about the specific conditions inside the rotating vortex that drove the extreme wind speeds the instruments were trying to document. Getting close was the methodology. The science was the answer to questions that the instrument's data addressed. Tim's peers in the atmospheric science community valued TWISTEX for exactly this reason. It was producing data that no other program was producing, not because Tim was luckier or braver or more willing to take risks, but because the specific combination of engineering skill, field methodology, and accumulated chase intuition that he had developed over 22 years created a capability that existed nowhere else. The turtle probes worked because Tim had built them to work. The intercepts succeeded because Tim had the judgment to position them correctly. The data was unique because no one else had assembled the same package. The program had a safety record across more than a decade of intensive field operations that reflected Tim's specific ethos. He was not, by the accounts of people who knew him well, a person who confused proximity with courage or confounded risk-taking with scientific value. He was precise. He assessed situations systematically. He turned away from intercepts that did not meet his criteria. He established the program's methodology around the principle that the instruments could only be deployed if the chaser was alive to deploy them. The data only had value if the scientists who collected it came back to analyze it. The specific operational evidence of this ethos was the safety record itself, more than 125 tornado intercepts over 10 years, involving direct, close approaches to some of the most violent atmospheric events on Earth, and no serious injury to any TWISTEX team member. 0. The closest calls were close. And Tim talked about them with the honesty of a scientist who understood that the methodology's validity depended on not deceiving yourself about its limits. But 0 serious injuries across 125 tornadoes is the record of a program that managed risk rather than ignored it. That record ended on May 31, 2013. Carl was 45 years old at the time of his death, a California native who had made his way into tornado science through a path that combined technical skills with the specific patience that scientific fieldwork requires. He appears on screen in the Discovery Channel footage, as a measured, careful presence alongside Tim's more publicly prominent role as the program's founder and director. What Carl Jung brought to TWISTEX was not simply the technical skill to operate a camera and coordinate communications in the field, though both of those skills were real and necessary. He brought the decade of accumulated experience that only comes from having done something consistently, in all its variations and failures and partial successes, and rare complete successes. For 10 years alongside the person who designed the whole endeavor. By 2013, Carl had been part of over 100 tornado intercepts with Tim. He knew the positioning logic from the inside, not as theory, but as the specific practice judgment of someone who has seen the methodology work and fail and work again across hundreds of deployments. He knew Tim's thinking well enough to anticipate it. He knew the instruments well enough to be useful to them at the moments when being useful to them mattered most. Tim Samaras' peers talked about his uncanny ability to predict the path of a tornado, the intuitive reading of a developing storm that experienced chasers develop over years in the field, and that allows them to position correctly for intercepts that look, to outsiders, impossibly precise. Carl Jung had spent 10 years watching Tim make those predictions and learning to calibrate his own judgment against them. He was not simply a passenger in the TWISTEX program. He was a collaborator who had been present for the entire arc of the project's most productive decade, and whose contribution to that decade, in fieldwork reliability, in video documentation, in the human dimension of maintaining a functional long-term research team in an environment as physically and psychologically demanding as tornado chasing, was real and specific, even if it was less visible than Tim's headline achievements. 125 tornadoes over 10 years, together. That number belongs to both of them. Paul Samaras was 24 years old on May 31, 2013. He was Tim's son. The specific biographical fact of a father and son in the same vehicle, chasing the same storm, dying in the same moment, is not something that tornado science had encountered before and has not encountered since. Paul had come into TWISTEX field operations not because he was pushed into it, but because the work was his father's. And his father's work was part of his life from the beginning, and as he grew older, the boundary between watching his father's passion and participating in it became easier to cross in one direction. His role in the field was videographer, the same functional role that the program needed someone capable and reliable to fill, the same role Carl Jung held in his own capacity. Paul's contribution was real. He was not there as a symbolic heir or a cherished passenger. He was there because he had the skills the operation needed, and because the people in the vehicle with him trusted those skills. The relationship between Tim Samaras and Paul Samaras that brought them both to a county road in Canadian County, Oklahoma, on the afternoon of May 31, 2013. Is a relationship that most people can understand in its basic emotional logic, even without knowing tornado science. A father builds something over a lifetime. A son grows into it. At 24, Paul Samaras had grown into TWISTEX field operations far enough that his presence there was professional as well as personal. He was his father's son on that road. He was also, in the specific terms of the program's operational structure, a contributing member of a research team that had been doing this work for a decade. 24 is young, 55 is not old. Neither had finished what they started. The 2013 season had already produced one of the most significant decisions of Tim Samaras' career before Reno. On May 20th, 2013, 11 days before May 31, an EF5 tornado struck the city of Moore, Oklahoma, killing 24 people and causing catastrophic damage across a wide swath of suburban Oklahoma City. The tornado was the same general category as the storms that Tim Samaras had spent 22 years studying and measuring. The atmospheric setup in advance of the event was clear. The Storm Prediction Center had issued severe weather outlooks, placing the Oklahoma City corridor under elevated tornado risk. The developing storm was accessible from the road network south and east of Moore. It was a chase day. Tim Samaras looked at the specific parameters of the storm, the road network geometry relative to the anticipated track, the population density of the suburban environment the tornado was tracking through, the predicted storm speed and direction, the developing intensity, and made a judgment call. He decided the conditions were too dangerous to attempt an intercept. This was not a decision made from the safety of distance, from an office reviewing radar imagery after the fact. It was a decision made in the field, by someone who was present and who had the equipment and the experience to go, and who chose not to go. The specific factors that led Tim to this conclusion have been reconstructed from accounts of his thinking from colleagues who knew him. The suburban environment of Moore, with its dense road network and multiple competing traffic flows from residents evacuating, created positioning problems that the open rural road networks of Kansas and Oklahoma farmland do not present. The storm's speed and intensity made the window for safe intercept and escape narrower than Tim's operating criteria permitted. And the specific tornado that killed 24 people in Moore on May 20, an EF5 that carved a mile-wide path through a densely populated area, destroying thousands of homes and 2 elementary schools, was the kind of storm that even Tim Samaras' 22 years of experience identified as beyond the safe operating envelope of the TWISTEX methodology. He watched the Moore tornado from a safe distance. He came home. His family's other children, his wife Kathy, the people who would survive the spring of 2013 to attend his memorial, they were relieved. 11 days later, on May 31, 2013, Tim Samaras and Carl Young and Paul Samaras drove out again. The Storm Prediction Center had issued a high-risk forecast for western and central Oklahoma, the highest category on the probability scale. The storm that developed west of El Reno appeared to offer workable intercept geometry on the available road network. The tornado that formed initially was significant but not obviously beyond the operational envelope of a team with their experience and methodology. They positioned east. The specific thing that made El Reno lethal for the TWISTEX team is not that they made a mistake by choosing to chase it. It is that El Reno became something different from what it appeared to be in the minutes between when they positioned east and when the subvortex reached their car. The tornado they positioned for was a workable storm. The tornado it became was the widest tornado in recorded history, expanding from 1 mile to 2.6 miles in roughly 30 seconds, executing a left turn that no operational forecasting tool available in 2013 could have predicted with sufficient lead time to matter, generating subvortices whose intensity and reach extended the hazard zone beyond what the radar returns showed. Tim's uncanny ability to predict the path of a tornado, the quality his peers talked about, the intuition developed across 22 years and 125 or more intercepts, was calibrated against tornadoes that behaved within the operational envelope of prior chasing history. El Reno exceeded that envelope, not because of a judgment error, because it exceeded the envelope. The distinction matters. Tim Samaras had not lost his judgment by May 31, 2013. He had, 11 days earlier, demonstrated that his judgment was still functioning correctly by correctly identifying a storm as too dangerous to chase. El Reno was not a failure of judgment. It was an encounter with a storm that violated the assumptions underlying the best methodology available, an encounter that, by the time those violations became visible in the data, had already occurred. The subvortex reached the Chevrolet Cobalt. The specific sequence that followed is documented in what the physical evidence left behind, and in what the position data from the vehicle's last transmission shows. The TWISTEX Chevrolet Cobalt, the mobile mesonet vehicle, the car that had carried Tim Samaras and Carl Jung and their instruments to more than 125 tornado intercepts across a decade. The car that had parked at the side of county roads in Kansas and Oklahoma and South Dakota, while Tim dropped probes on the pavement in front of approaching storms, was caught by the subvortex of the El Reno tornado's circulation. A subvortex is a smaller embedded rotation within a larger tornado's circulation, and the one that reached the Cobalt was carrying wind speeds that the post-event analysis of the mobile Doppler radar data suggests were consistent with EF5 conditions, above 200 miles per hour, in a zone that extended well beyond what the main circulation's visible radar footprint had indicated. Paul Samaras was ejected from the car. Carl Jung was ejected from the car. Tim Samaras was buckled in the passenger seat and was in the car when the car was thrown to the position where it was later found. That position was approximately half a mile from where the team had last transmitted. Half a mile. The car Tim Samaras had spent 22 years building a career to put in the right position relative to tornadoes was half a mile from the right position when everything stopped. It was the first known instance in the history of American tornado science of a storm chaser or meteorologist being killed by a tornado. Every professional who had chased tornadoes, who had positioned vehicles relative to supercell circulations, who had placed instruments in the paths of violent storms and driven away before the storm arrived. In the entire documented history of the modern tornado research community, no one had been killed by a tornado doing this work. Not one. The methodology worked across decades of accumulating practice until May 31st, 2013. When it encountered a tornado that violated its governing assumptions simultaneously and by margins that the available data did not communicate in time. The safety record that Tim had maintained across his 22 years and 125 plus intercepts was not a product of luck. It was a product of the specific calibration he brought to every chase decision, the same calibration that had told him 11 days earlier that more was too dangerous. What that calibration could not account for was the specific combination of parameters that El Reno assembled in real time and presented to a team that was already committed to a position based on how the tornado had looked 60 seconds before it stopped looking that way. Richard Charles Henderson, a Hinton, Oklahoma resident who had decided to follow the storm on his own, who had photographed the El Reno tornado from his phone in the seconds before it reached him, was also killed in the same area. His photograph of the storm exists. His presence in the same zone as the TWISTEX team at the same moment, for different reasons, is a reminder that the El Reno tornado's deviation from its expected path did not discriminate between researchers and bystanders. The storm went where it went. The broader storm, chasing community's response to Tim Samaras' death, was specific and personal in a way that most community grief is not, because Tim was not simply a famous name in the field. He was the person many of them knew as the standard against which their own field judgment was calibrated, the person whose safety record and methodology had seemed to demonstrate that experience and preparation and the right instruments could maintain the necessary margin between a close approach and a fatal one. His death did not prove that wrong in any simple way. It established instead the specific condition under which the margin collapses, when the tornado becomes something different from what the positioning decision was made for, faster than the road network permits a response. The chasing community has been navigating that knowledge ever since. What ended on May 31, 2013, was not just 3 lives. It was TWISTEX. The program that Tim Samaras had built from a 50-pound prototype probe in a Denver workshop into a decade-long scientific program with 18 National Geographic grants, a Guinness World Record, approximately 12 peer-reviewed papers, and a body of tornado interior measurements that no other program in the world had collected. That program required Tim Samaras to exist. His specific combination of engineering skill, atmospheric intuition, accumulated field experience, funding relationships, and the respect of the scientific community that made the collaboration with Iowa State and the University of Northern Colorado possible, this was not a package that transferred to someone else when the program's founder died. The TWISTEX researchers who survived May 31, 2013, discussed plans for future operations in 2015. Those operations did not occur. The probes, the instruments that had survived direct passage of F4 tornadoes, that had measured the greatest pressure drop ever recorded inside a tornado, that had given atmospheric science the first direct measurements of what the interior of a tornado actually does at the surface, became museum pieces. Not because the scientific questions they were designed to answer had been answered. Not because a better instrument had replaced them. Because the person who built them, deployed them, interpreted the data they produced, and had the field judgment to position them correctly, was not there anymore. The interior of a violent tornado is once again in the formal language of the observational record, as data sparse as it was when Tim Samaras began building instruments in 1999. Atmospheric scientists studying tornado thermodynamics still work primarily from computational models and from the indirect inferences that radar, drops-on balloons, and surrounding environment measurements allow. The direct in situ data from tornado interiors that Probe 3 captured on June 24, 2003, and that subsequent TWISTEX deployments added to, is now a historical dataset, irreplaceable, unique, and not being extended. The gap in the observational record that TWISTEX was designed to fill has not been filled by any successor program. There is a specific scientific irony in this. The data that Probe 3 captured at Manchester, the 100 millibar pressure drop, the temperature and humidity measurements inside an F4 circulation, generated scientific papers and informed atmospheric models and advanced the understanding of tornado thermodynamics. But it also demonstrated that the measurements were possible, and that demonstrating they were possible was not the same as having a permanent institutional infrastructure capable of continuing to make them. TWISTEX was Tim. Without Tim, TWISTEX ended. The Discovery Channel's Storm Chasers ran for 3 seasons. When it was cancelled in 2012, Tim Samaras was still alive and TWISTEX was still active. The show that had introduced him to a broad public audience ended the year before he died. Tim's obituary in the November 2013 issue of National Geographic, the magazine that had funded his work through 18 grants, that had sent Karsten Peter to photograph his chase in South Dakota in 2003, that had featured him 4 times across 9 years, described him as a courageous and brilliant scientist who fearlessly pursued tornadoes and lightning in the field in an effort to better understand these phenomena. Weather Channel meteorologist Jim Cantore called it a very sad day for the meteorological community and the families of our friends lost. The meteorological community's loss was real in the specific way that the death of an irreplaceable capability is real. When a scientist dies, their knowledge and publications remain. When a program that depended on a specific individual's combination of skills dies with them, the knowledge and publications remain, but the future data does not. The Guinness record from Manchester, South Dakota, June 24, 2003, still stands. The greatest pressure drop ever measured in a tornado, 100 millibars in approximately 12 seconds, recorded by Probe 3 at the intersection of 207th Street and 425th Avenue in Kingsbury County, South Dakota, 82 seconds before the F4 tornado reached the instrument's position. The physics that pressure drop records is foundational. The pressure deficit inside a tornado's rotating vortex is the mechanism that drives the extreme wind speeds. Air accelerates inward from the higher pressure surrounding environment toward the low pressure core. And the rotation of the vortex converts that inward acceleration into the tangential wind speed that destroys structures and kills people. The magnitude of the pressure deficit is directly related to the maximum wind speed at the vortex surface. A 100 millibar pressure drop in the core of a tornado corresponds, in atmospheric physics, to wind speeds that place the event solidly in F4 territory. Tim's probe measured this from inside the event, directly, in real time, at 10 samples per second. No atmospheric model had produced this measurement. No radar remote sensing had produced it. A 50-pound armored instrument placed on a county road 82 seconds before the tornado arrived produced it, because Tim Samaras built an instrument that could survive being there. The scientific community's response to the TWISTEX data, in the years between Manchester and Reno, was to incorporate it into the research literature in a specific and important way, as the calibration target that no other data source could provide. Atmospheric models of tornado thermodynamics are built on assumptions about what the interior of a tornado's vortex does, assumptions that, before Probe 3's data on June 24, 2003, had to be parameterized from theory rather than observation. After Manchester, the model assumptions could be tested against a real measurement. The data was too limited in scope: one probe, one tornado, one location in the vortex at one point in time, to answer all the questions atmospheric modelers had about tornado interiors. But it was enough to tell the field something specific, that the measurements were possible, that the assumptions were at least partially testable, and that a systematic program of probe deployments across many tornadoes over many seasons could eventually produce the dataset the models needed. That systematic program was TWISTEX. It ended with 3 deaths in Canadian County, Oklahoma on May 31, 2013, before the dataset it was designed to assemble was complete. Globally, the story of Tim Samaras is taught in tornado research courses and atmospheric science programs as the specific example of what an individual scientist with a clear problem, the right engineering skills, and sufficient determination can accomplish, and of the specific risk that scientific fieldwork at the extreme end of hazardous atmospheric events carries. The countries where tornado science is most active, the United States, Canada, Bangladesh, Argentina, parts of Europe, have each in their own way encountered the question of how to obtain in situ tornado measurements. And the TWISTEX program and its Manchester data are the reference point that each of these research communities starts from when they think about what direct tornado interior. Measurement requires. The Brantley Hargrove biography of Tim Samaras, The Man Who Caught the Storm, published in 2018, drew on interviews with Tim Samaras, Tim's daughters, and his TWISTEX colleagues, as well as on hours of Tim's own chase footage spanning from 1991 to 2013. The footage that Tim himself recorded across 22 years of chasing, the specific visual and audio record of how he thought, how he positioned, how he talked about the storms he was pursuing, is a primary source for understanding not just what TWISTEX accomplished, but how the person who built it actually worked. Hargrove described sitting beside Tim in the car in the footage Tim had filmed himself across those 22 years, listening to what he heard and seeing what he saw. In that footage, according to Hargrove's account, you can watch Tim Samaras working through a tornado intercept in real time, making the decisions, adjusting the position, talking through the storm's behavior, in a way that conveys the specific combination of technical knowledge and intuitive read that made TWISTEX possible. It is not a person being reckless. It is a person being precise. His widow, Kathy, continued ChaserCon, the annual National Storm Chasers Convention that Tim had founded in 1998 and that had grown over 15 years into one of the most significant annual gatherings in the storm chasing community. The convention that Tim had started as a small gathering of people who shared his specific passion for being in the field near violent atmospheric events became, after his death, one of the places where the storm chasing community collectively processed what El Reno had established and what it meant for the community's future. The hundreds of chasers and researchers and meteorology students who attended ChaserCon each year found in its continuation after Tim's death one specific institutional expression of the commitment that Tim's work represented: that the study of violent storms, done with precision and preparation and the right instruments, is worth doing, even knowing what the work can cost. The three who died on May 31, 2013, are documented in the scientific record through their contributions: Tim's peer-reviewed papers in the Guinness Record probe data, Carl's decade of fieldwork and Discovery Channel documentation, Paul's presence as a videographer across multiple seasons of TWISTEX operations. The documentation does not fully capture what they were as people. The father, who was also an explosives engineer, who also photographed lightning, who also built the instruments that measured the inside of an F4 tornado. The California native who spent a decade in the Oklahoma summers chasing storms alongside the person who built the measuring program from scratch. The son who chose to be part of his father's life's work at 24. In a field that requires years to develop the intuition that keeps people safe, and who was part of it the day the methodology's limits were reached. The limits were reached on a county road in Canadian County, Oklahoma, at approximately 6:15 p.m. on May 31, 2013. The car was half a mile from the last transmission. Carl Young, 45, California native, 10 years of tornadoes alongside Tim Samaras. A decade of county roads and mesonet vehicles and probe deployments, and the accumulated work of being the person in the vehicle beside the person who built it all, was ejected from the Chevrolet Cobalt when the subvortex reached the car. Paul Samaras, 24, Tim's son, a young scientist who had chosen to inherit his father's life's work at an age when most people are still finding out what their life's work will be, was ejected from the Chevrolet Cobalt when the subvortex reached the car. Tim Samaras, 55, passenger seat, buckled in, the explosives expert who became an amateur astronomer, who became a lightning researcher, who became a tornado scientist, who became the only person in the world who had measured the greatest pressure drop ever recorded inside a tornado, was in the car when the car was thrown to the place where it was found, half a mile from the last transmission. He had been right about more. He had been right about 125 tornadoes before El Reno. He had built instruments that survived direct passage of F4 tornadoes and kept recording. He had placed those instruments within 100 yards of approaching funnels and escaped north. He had done this for 22 years and come back every time with the data. To a family and a workshop, and a program and a record that still stands in the Guinness Book. The interior of a violent tornado is waiting for whoever builds the next instrument capable of measuring it from inside. That person will be starting from what Tim Samaras left behind.